Germany-based Carl Zeiss AG is a fascinating company. Fascinating even if you do not take into account that they make lenses and optics for some of the coolest systems in the world. When you are etching patterns as wide as a small virus, you have graduated beyond simple lenses. Now we have to call them optics systems. These massive multi-component systems are at the very heart of the multi-million-dollar photolithography machines that ASML makes. Without them, ASML has no machine for TSMC, Samsung, or Intel. In this video, we're going to continue with our deep dive into the semiconductor industry's critical suppliers with a look at one of ASML's closest partners, the makers of the optics systems that let high-energy UV light etch wafers, and a company with an utterly fascinating history, Carl Zeiss. But first, I would like to ask if you might be interested in the Patreon. If you like what this channel does, you can support the work by joining the Early Access tier. Early Access members get to see videos long before that they are released to the public. So head on over to the Patreon page and take a look. I deeply appreciate anything you'd be able to sign up for. Thank you, and on with the show. This company and its history is fairly well documented in Wikipedia, and I recommend that you read it. The company that would eventually become Carl Zeiss AG was founded in 1846 by Carl Zeiss, a German scientific instrument maker. Born in 1816 in Weimar, Germany, Zeiss was one of 12 siblings. He was born into a family of artisans, and in 1846, Zeiss set up a microscope workshop. There, he would repair university equipment, make microscopes, and sold scientific instruments like eyeglass lenses and thermometers. His workshop did well under his exacting care and soon expanded. In 1866, Zeiss recruited Ernst Abbe, a brilliant 26-year-old physicist from the University of Jena. Abbe's insights on the movement of light rays through microscope lenses helped the company to move beyond crude trial-and-error manufacturing and gave it a leg up on its competitors. Zeiss died in 1888, but the company continued to grow over the years. Abbe took over and founded a series of new business lines in search of diversification. Zeiss moved into measuring instruments, camera lenses, binoculars, telescopes, and more. This diversification helped the company grow and survive the turmoil of the 1800s. By World War I, the company was making military optics products like binoculars, periscopes, and gun sights. They were the world's largest maker of cameras at the time, but 80% of the revenue came from military products. This probably had not been the founder's intention, but such is the case with many companies. The company has a very interesting ownership situation, to say the least. After Zeiss's death, Dr. Ernst Abbe purchased sole ownership of the company from Carl's son. He then transferred his ownership to what is now called the Carl Zeiss Foundation. I'm not even going to try to pronounce it in German. He then wrote into the foundation guidelines a variety of social reforms like health insurance, pensions, profit sharing, equality in hiring decisions, overtime pay, and 9-hour workdays. The foundation has no owners or shareholders, but Abbe did not want to create a nonprofit. Rather, he wanted to guarantee that the company would continue to exist after his death and that its employees can partake in its economic success. The company was told to optimize for long-term economic success, and any excess profit would be invested into the working population of the city of Jena. So more like a cooperative than a charity, which is pretty interesting since most cooperatives I know of are more like pizza shops than high-tech companies. Imagine Google being set up as a cooperative. In the 1930s, the Nazi Party attempted to put a representative inside the foundation, but they resisted. Eventually, a compromise was reached. The foundation board members became nominal members of the Nazi Party in exchange for independence. At the end of World War II, the United States Army first arrived at and occupied the city of Jena in 1945, but soon had to withdraw as the city fell within the Soviet zone of influence. As part of a policy to bring leading German scientists under American control, the Americans quickly spirited away 130 of the company's top technicians and executives. They would be resettled in the West German city of Oberkochen. The board members, having been Nazi Party members during the war, readily agreed. These critical individuals would go on to rebuild a factory and the company from memory alone. At first, there was hope that the company could remain together. But then in 1947, the Soviet Army shipped 94% of Zeiss's Jena-based equipment as well as 300 of their employees back to the Soviet Union as war booty. These would later help found the Kiev brand of cameras. So now we have Zeiss in West Germany, which started off as Opton but then became Zeiss Oberkochen. And then we have Zeiss in East Germany, often called Zeiss Jena or VEB Carl Zeiss Jena. The VEB stands for state-owned enterprise. The two operated separately over the next few decades, offering the same products and battling out in overseas court over who owned the trademarks overseas. Eventually, after 18 years, the two split the world in half and agreed not to use the Zeiss trademark in each other's half of the world. They can still operate there, just not use the Zeiss name. Zeiss of West Germany would use the name Opton in Eastern Bloc countries. Zeiss of East Germany went with something called Ostjena in Western Bloc countries. Due to their respective circumstances, both companies started off with nothing, but still flourished over the years. There is definitely an interesting future video about how the two companies fared under socialist and capitalist regimes. Zeiss Jena in particular became an East German flagship company, diversifying into new areas like military technology, space technology, and semiconductors. Then came German reunification. Zeiss Jena found itself in trouble. It had substantial overlap with its Western sibling, but was at an economic disadvantage, having lost the critical Soviet military market. These were economically turbulent times. Reunification was messy. East German industrial output fell by 51% from the previous year. 3 million East Germans would lose their jobs. West German companies were raiding Eastern companies for their best parts. Amongst all this, Zeiss Jena negotiated with its Western brother over its future. After many years, a settlement decided that the East German parts of the traditional Zeiss company, microscopes, medical instruments, whatnot, would be acquired by the West German part, as well as the name. The remainder, a 6,800 employee diversified firm, now renamed to Jenoptik, operated in semiconductors, laser optics, and automation. At first, it was in danger of collapsing, but then the government stepped in, buying 80% of the assets and saving thousands of high-paying jobs. In 1998, the company conducted a $400 million USD IPO and is doing well today. Today, Carl Zeiss AG is a large, sprawling company. They have 4 segments: industrial quality and research, medical technology, consumer markets, and semiconductor manufacturing. These various divisions provide optical systems for industries as varied as consumer eyeglasses, cars, medical surgeries, and measuring machines/microscopes. Like many of the other companies that I have discussed in this channel, Carl Zeiss spends a whole lot on R&D, 812 million euros in 2020, or 13% of their entire revenue. Considering the sophistication of their products, it makes sense. For the rest of this video, we're going to focus on the products in their semiconductors manufacturing division, Carl Zeiss SMT. A large portion of the world's microchips are made using Zeiss technologies. The company is a joint venture between Carl Zeiss AG, which has majority share, and ASML itself, who has a 24.9% stake in the business per their annual report. The company's core product here are the optics at the heart of the lithography scanners and steppers that ASML makes. Let's get started with DUV. Deep ultraviolet lithography, or DUV, uses ultraviolet light rays in the 193 nanometer or 248 nanometer range. DUV techniques power the majority of process nodes today. Zeiss, the company, has been building deep ultraviolet imaging systems for nearly 100 years. Carl Abbe himself had proposed the possibility of a microscope using ultraviolet light as far back as 1874. But it would not be until 1899 that the company was able to develop a quartz lens suitable for UV microscopes. In the 1960s, the company embarked on leveraging its microscope techniques to build a lens for microlithography. This was the first time that any such lenses had ever been made. Microlithography requires that light distortions be controlled very tightly across a relatively large space. Makes sense since you do not want your IC design to be inaccurately transferred onto the silicon. One lens turned out not to be enough, so Zeiss combined multiple smaller lenses together to create a big, massive optics system. And look at how the multiple lenses are arranged together into this double bulge structure. This funny looking bulge and waist structure reduces field curvature, which is a common optical problem that causes objects to be sharp only within a certain area in the frame. It cannot all be in sharp focus simultaneously. What that means in lithography is that if you are trying to project a design across too large of an area, field curvature can cause inaccuracies at the areas of the frame where they are not sufficiently sharp. Throughout the 1980s and 1990s, Zeiss borrowed and mixed together new tricks from their microscope work to accommodate changes in the industry and increase the resolution at which they are able to project an IC design onto the wafer. Then, in the 2000s, the discovery of immersion lithography allowed for the next breakthrough in resolution improvement. Previous lithography techniques had an air gap between the wafer and the stepper. Seems simple enough. Immersion lithography replaces that with water. So now you are shooting ultraviolet light through water at silicon. First proposed and validated for semiconductor use by Taiwanese scientist Bern Lin, the technique allowed foundries to etch structures as small as 40 nanometers. Today, Zeiss's top products for this lithography technique are the Starlith 1900 series, including the 1900i. They are some of the company's top-selling products ever. The company invested over 450 million euro into a brand new factory and had to overcome substantial new engineering challenges so to build this specific optics system. Extreme ultraviolet lithography, or EUV, is the next step in the semiconductor fabrication roadmap. It is a disruptive technology used in today's cutting-edge process nodes. The fact that it is using a brand new wavelength requires a lot of radical changes to the optics system. The key issue is that all available materials can absorb high-energy UV light, including the air itself. This means lenses are not possible. The UV light would not be able to pass through them. Thus, Zeiss would have to craft an optics system entirely out of multi-layer mirrors. Zeiss first began working on its EUV optics system with the initiation of a micro-exposure tool in 1995. You can think of it as a smaller version of what the final tool would be, like a mini horse. Collaborating with the Lawrence Livermore National Lab and Berkeley Lab in California, they delivered the first prototype in 2003. They continued to refine the design 5 times over the next couple years. In 2015, the first full-field EUV optics system, named the Starlith 3100, was delivered for ASML to put into their ASML ADT NXE 3100, ADT meaning Alpha Demo Tool. Gamers complain about paying for early access. Look at Intel and TSMC, paying millions for an early access alpha demo tool. The Starlith is a multi-component system that consists of collector optics, an aperture, illumination optics, reticle, and projection optics. First, light from the EUV light source hits the collector, which collects and then projects that light through the aperture at medium focus into the illuminator. The illuminator spreads out the light evenly. The now uniformly illuminated light then reflects off the reticle, which contains the IC chip's designs, and is then finally projected onto the wafer. The 3100 pioneered the optical system's core mechanics, which would be later refined in further releases like the Starlith 3300, 3400, and so on. Today, it makes up a critical part of EUV-based process nodes at 7 nanometers or lower. Carl Zeiss is a large company that owns many other divisions and is involved in many things. For this video, I only focus on the aspects involved in semiconductor manufacturing, but the other divisions are also very much worth studying. In 2020, the semiconductor division made 1.8 billion euro in revenue. It grew 12% year over year, while the rest of the group's divisions saw revenue declines due to the pandemic. Today, it contributes 30% of the group's business and holds critical strategic importance in German industry. The group's unique ownership structure ties it to its community in a way I don't often see in the United States. Being a critical strategic partner alongside ASML, the company is basically the only one of its type. Japan-based Nikon and Canon, ASML's closest competitors, make their own optics systems for their lithography devices, an arrangement that did not work as well as what ASML and Zeiss have. As part of the research for this video, I briefly took a small peek into how Zeiss's DUV and EUV optics systems worked. To be honest, it was one of the most difficult things that I have ever read. This is a fantastically complicated artisan system, and it makes me wonder how Nikon, or anyone else for that matter, can catch up. Alright everyone, that's it for tonight. Thanks for watching. If you want more content, you can like and subscribe to the channel. I would appreciate it if you did. And remember to hit up the email newsletter and sign up. Want to send me an email? Drop me a line at john@asianometry.com. I love getting letters from viewers. Until next time, I'll see you guys later.